Morning. My name is Raymond Morgan. I think many of you already know me, but there may be some that don't. So a little background. I'm an ADEQ employee that retired a few years back and been brought back as a contractor to provide some training and technical support. And so this morning I would like to talk about chlorine disinfection. It's a very common method of disinfection used for on-site wastewater treatment facilities. And so my title of my presentation is Chlorine Disinfection Explained. And I saw a need for this explanation because so often, as I've looked at in the past design reports and looked at what the engineer was submitting, they basically just calculated how many tablets were being consumed, and that was about it. And I wanted to give more information as to what the chlorine disinfection process really is. So I want to give you some information about that to understand it better. We're going to look at some key terms, what those mean. And then we're going to look at another presentation. We're going to do some calculations, calculate the detention time. And then we're also going to look at an Excel spreadsheet that's been developed to allow you to calculate the number of tablets that might be consumed with associated with a given flow and a given disinfection dose. So with that, let's take a look at a summary of the various presentation topics that I want to try to cover today. And so first, we're going to look at a schematic of a typical on-site wastewater treatment facility. Just to look at the elements that typically are associated with a chlorine disinfection unit. Next, we want to look at some of the rule considerations associated with the type 4.20 permit. So we'll look at rule a little bit. Then we're going to look at some general information on chlorination. We want to consider some of the advantages of using chlorination as a disinfection process. We're going to look at some specific process details associated with chlorination. And we're going to look at some efficient use guidelines of the chlorination process. These will be qualitative guidelines to give you some idea of when the chlorination will be more effective or less effective. And then we're going to look in more detail at a chlorine tablet disinfection device. Look at some diagrams of that, some issues associated with that may be cause for concern. Then I want to talk about a warning about using pool chlorine tablets in a wastewater effluent disinfection device. And hopefully that you can share this information to permittees and that, and there's significant danger to using these pool chlorine tablets in a wastewater effluent disinfection device, and we'll explain that in more detail. So first, here is schematic, and so let's get a. So we have first the wastewater treatment facility itself, and then effluent, and it's actually still labeled as wastewater, even though it's much better quality than it was at the inlet side of the treatment plant. So then we have your typical tablet disinfection unit at this point. Sometimes, there's one particular manufacturer, they actually incorporate the disinfection, chlorine disinfection device in the treatment plant itself. And then you have your pump tank and your contact tank, and usually those are combined. This one manufacturer, they actually have a contact tank built in. And then usually you have it going to a subsurface drip disposal field. It doesn't necessarily always have to be, but that's usually the case. So let's go back. So the type 4.20 permit allows for the use of a disinfection device if the effluent has a value for total suspended solids of 30 milligrams per liter or less, and complies with the following. So first, I want you to stop and take note of the fact you can only use disinfection with better quality effluent, namely 30 milligrams per liter or less. And then it needs to comply with the following few things here. First, the disinfection device kills the microorganisms by exposing the wastewater to heat, radiation, or a chemical disinfectant. So chlorine right now that we're going to be using qualifies under the chemical disinfectant. Second, some means of disinfection is required before discharge. In other words, there's got to be a need for disinfection as far as making use of a type 4.20 permit. Third, a reduction in harmful microorganisms as represented by the total coliform level is needed for surface or near surface disposal of the wastewater, or reduction of the minimum vertical separation distance specified in R18-9-A312E that's desired. And that's usually why I think we tend to see it mostly in subsurface drip, which is used because there are these type of issues that's prompting the use of the subsurface drip system. Okay, now let's look at some general information. Number one, chlorine is one of the most practical and widely used disinfectants for wastewater. Number two, chlorination is commonly used because it can kill disease-causing bacteria and control nuisance organisms such as iron-reducing bacteria, slime, and sulfate-reducing bacteria. Chlorine destroys target organisms by oxidizing the cellular material of the bacteria. And now chlorine can be supplied in many forms and can exist in liquid, solid, or gaseous phases. We're looking at the solid phase, calcium hypochlorite. And common chlorine-containing disinfection products include chlorine gas, chlorine compounds in solid or liquid form, liquid sodium hypochlorite, and solid calcium hypochlorite tablets are the most common forms of chlorine used for small systems because they're less hazardous than chlorine gas. Now let's consider some advantages why it's such a good idea to use chlorination. So chlorine is reliable and effective against a wide spectrum of pathogenic organisms. It can remove 98 to 99% of the microorganisms and wastewater effluent at, note this, the proper concentration and contact time. Both of those go together. All right, chlorine is more cost effective than UV or ultraviolet light disinfection or ozone disinfection. The chlorine residual that remains in the wastewater effluent can prolong disinfection even after initial treatment and can be measured to evaluate its effectiveness. Now let's look at some of the details of this process now. And there's some key terms that you need to understand. You have the chlorine dose. So I have the chlorine dose. Then we've also got chlorine demand. And then we got chlorine residual. As we're going to look, so we're dosing our effluent, our wastewater effluent, at a certain amount. But then there are things in that effluent that create a demand that is going to consume some of that chlorine dose. And then you're going to have the chlorine residual that's left over to do the disinfection. So now we'll go back and we see chlorine is added, but then chlorine is reacting, as I mentioned earlier, to these elements that are in the wastewater effluent. There are organics and there are inorganics. So now then that chlorine is consumed, which is known as chlorine demand. Okay, so now go back, look at our little diagram again. Chlorine is added. Now it's going to react with either organics or inorganics. So it's being consumed. So first thing we need to look at in more detail, what are these inorganic substances that will consume the chlorine? And there are actually several of them, and they'll take precedence in reacting with the chlorine. And they are hydrogen sulfide. So if your wastewater effluent has hydrogen sulfide in it, then it's going to react to it and consume it. If it has ferrous iron, it's going to react to it. Maybe your background water supply has a high iron content. That's an inorganic compound that's going to react with your chlorine. Manganese is going to react with the chlorine to consume it. Nitrite is going to act. All those are inorganic substances. Now, ammonia, NH3, is also found in all wastewater and is the second level of reaction with chlorine. It combines with chlorine to form one of three forms of chloramine. The chloramines act as disinfectants, and the three forms are monochloramine, dichloramine, and trichloramine. And then finally, the last one, organic compounds are the last to react with available chlorine in the wastewater and form chloroorganic compounds. So these compounds have only a very slight disinfection capability. So maybe kind of a summary here, the chlorine and combined forms that have disinfection properties plus any free chlorine is the chlorine residual. It is this component of the applied chlorine that is available for disinfection. Now, the residual is available in three forms. We have the chloramines, that's a form of combined chlorine. We have the chloroorganic compounds, that's a weak form of combined chlorine. And then finally, we have free chlorine. That's the strongest form of residual for disinfection. So now we want to look at this chemical process in a graphical form. So let's look at this in more detail. So on the y-axis, we have the chlorine residual as it goes from 0 on up. And then on the x-axis, we have the chlorine dosage, so it goes from 0 on up. And then we see the reaction process described here. And so initially, see here, initial chlorine demand, it's burning up all our chlorine. So as we're dosing it, there is no residual, and yet the chlorine is being consumed. Okay, now we burn up all of the initial chlorine demand. Now we start to see the combined residual chlorine, where the ammonia is kicking in. And now that is starting to climb up. And then that reaches a peak, and we're continuing to add chlorine. Now those combined residual materials, the chloramines, now they're being oxidized and burned up. And so then they fall back down, and then we reach a point which is known as breakpoint chlorination. And then as our dosage goes higher, the free chlorine residual then starts to climb on a 1-to-1 basis. As we increase our chlorine dosage by 1 milligrams per liter, our free chlorine residual increases by 1 milligram per liter. So that is what we're after. So in summary here, breakpoint chlorination is a point in the chlorination process at which enough chlorine has been added to satisfy the inorganic, ammonia, and organic demands of the wastewater. Once achieved, additional chlorine added to the wastewater results in a free chlorine residual. When this free chlorine residual is attained, the most effective disinfection can now take place. Now, in 2006, University of California at Davis, they did this study. They evaluated various disinfection units. And they cite that the results of chlorine disinfection at the point where free chlorine is available for disinfection is the critical point. So when that free chlorine was 1 milligram or more, the total coliform was measured as 0. And we're going to look at that study in a little bit. But first, I wanted to present several qualitative diagrams just showing where chlorine is effective. So we want the 1 milligram per liter, but we also want to consider some other factors qualitatively. So the first one is, what happens when the effluent has a given pH? Basically, the lower the pH, to the left, the lower it is, the more effective the chlorine is. As your pH increases, your effectiveness of the chlorination process starts to diminish. And I suggest you keep in mind the water quality, let's say, drinking water varies in its pH. So some parts of the states have a more alkaline water source. So there's going to be more chlorine needed to be effective in that. Okay, temperature. The higher the temperature, the more effective the chlorination process. And you'll see in the rule, for instance, if the wastewater is at 70 degrees Fahrenheit, rule specifies you need a detention time of 15 minutes. But if the wastewater is at 50 degrees Fahrenheit, the detention time is 30 minutes. And it's doing that because the chlorination process is not as effective in cooler temperatures. So if you're in a northern climate and you're doing disinfection and it gets down to 16 below 0 there, guess what? The chlorination process is not going to be near as effective in those temperatures. Okay, dosage, and that's, I think, pretty self-evident. As you increase the dosage of chlorine, the effectiveness is also going to increase. And then the longer your detention time, then the more effective your chlorination is going to be. And so now, as we consider efficiency and effectiveness, let's consider the type of organism that's going to be treated, because that's going to influence the efficiency of the process. There are some organisms that's easier to kill with chlorine and some that are very difficult. So first of all, viruses are killed quickly with chlorination. Second, bacteria cells are killed quickly. Now, cysts and spores may be resistant. And one well-known one is Cryptosporidium. That's very resistant. And so it depends on what type of pathogen you're dealing with on how effective your chlorination process is going to be. Now, I mentioned this study from the University of California at Davis. So they have this nice little table, and let's look at this and understand this table a little bit more. Okay, so they looked at 3 different things: this MS2, coliphage, total coliform, fecal coliform. And then they looked at, okay, when the free chlorine concentration was measured, when it's greater than 1 milligram per liter, look what's happened. You've got 0 CFUs for all 3 of these particular organisms. And notice it says all values reported or after a 10-minute contact time. So you need at least 10 minutes. They don't describe or give information about temperature, but I assume it was probably also around the 70 degrees Fahrenheit. Now, let's look at the actual chlorine tablet disinfection device itself. And what I'm showing here is a nice little diagram of a double stack chlorinator. So look at this. So we see the effluent comes in here, it traverses through, makes contact with our little tablets right here. There's little windows so that the wastewater effluent can make contact with the tablets. and then it exits here. So there's a profile view of it where you have a tube, feed tube. You can stack up a number of different chlorine tablets. And you see our little window coming in here, makes contact and goes on out. Now, this is a picture of what can happen. So obviously the chlorine tablets are breaking down higher up in the tube. Ideally, we want to break down just where they're coming into contact with water. I'm not sure what happened here. You know, it could have been humidity that did this. If there was a pluggage downstream or something, there was a backwater effect and effluent rose up into the tube. That's possible that would cause it. But the thing I want to stress here, some chlorine tablets are more prone to absorbing moisture from the air and will break down and adhere to the tube sidewalls and stop the disinfection process. I was talking with an individual that's a operator of these little on-site treatment plants and services and maintains them and so on. And he said this, he says, Raymond, I have found that the standard calcium hypochlorite tablet, 9 milligrams per liter dose, doesn't break down as much as the 20 milligram per liter tablet. And the 20 milligram per liter, they release more, but they tend to hang up on the sidewalls and some of this breakdown. So that's something you may want to keep in mind. That was just his opinion and what he had observed. But when I think about it logically, to release 20 milligrams per liter, you got to take a look at the binding agent, and you want to be able to release like a lot of the tablet quickly. And so it makes sense the binder might be not as strong as the 9 milligrams per liter tablet. But that's something to keep in mind, is what type of tablet, and monitor whether it could start having some problems breaking down in the upper part of the tube, feed tube. So now let's get to my chlorine tablet warning. Currently, there are two predominant types of chlorine tablets found on the market. There's calcium hypochlorite, and there's chlorinated isocyanurites. And there are two very different products. The calcium hypochlorite, which I put in parentheses, septic disinfection tablets, because in some places that's what they're called, septic disinfection tablets. That's very misleading, but nevertheless, that's the label. So these tablets are the only readily available tablet product labeled and approved for wastewater disinfection. They're very reactive and quickly kill bacteria and wastewater. 99% of the bacteria kill takes place in the first 10 minutes following contact. Just as important, the chlorine residual that is present in the water after disinfection will dissipate rapidly so that it does not damage the receiving environment. And I would say dissipate rapidly is a qualitative term relative to the pool tablet. All chlorine products are hazardous and must be handled with care. It's against the law and extremely dangerous to repack the tablets into a smaller container or plastic bag. And these tablets are also readily available at larger hardware or home improvement supply stores and are probably located in the plumbing department. I did some online searches and I found them. So it's not like they're not available. And just keep in mind that when you have calcium hypochlorite sealed up in a tight container and you pop that lid off and get a whiff of gas, you're getting a whiff of chlorine gas there. Be careful. Now let's look at the pool tablets. There are chlorinated isocyanurites, commonly known as swimming pool tablets. So these pool tablets, they're using a white tub with a yellow or orange top, can be purchased from swimming pool supply stores, discount retail stores, and mail order outlets. Due to their widespread availability, these tablets often make their way into wastewater treatment systems. though their use in these systems is both dangerous and illegal. These pool tablets dissolve more slowly than calcium hypochlorite and create a residual that does not readily dissipate, which you would want in a pool, swimming pool. And the tablets work well in swimming pools where clean water is continually recirculated and slow dissipation of the residual is desired. But they are unsatisfactory for wastewater treatment. Pool tablets will not thoroughly disinfect the effluent, and the chlorine residual remains for long periods of time and can damage the receiving environment. Now, let's look a little further here. The chlorine gas generated from the pool tablets can damage and rust the wiring in a wastewater treatment system from the effluent tank to the control box, making for a possibly expensive repair. An additional danger can arise due to an accumulation of moisture within the pool tablet. Designed to be totally immersed in water, pool tablets that expose to periodic flows of liquid begin to decompose and release an explosive gas called nitrogen trichloride. If a sufficient concentration of nitrogen trichloride builds up within the wastewater system, it could be ignited when exposed to an open flame, electric spark, or organic contaminants. These explosions can be devastating, causing extensive property damage and potentially serious injuries. So people do not want to use pool tablets and a wastewater treatment device. And I might mention, it's good practice on the control box and junction boxes and so on of sealing the inlets and outlets to those boxes. There's special putty compounds that can be placed in there to break the flow, even just of humidity going up into your control box and causing corrosion. And of course, I guess in a pinch, I guess you could use silicone caulk. But you really want to try to isolate those boxes. Any moisture or gases being able to work its way back up the electrical conduit into junction boxes and control panels and so on. Now, search topic title. I wanted to throw this one in here. I found it very humorous what type of titles these home improvements and hardware stores and whatever give to the calcium hypochlorite tablets. So if a search engine is used to see if a store has the proper wastewater chlorination tablets for sale, I suggest you search for septic disinfection tablets. However, you'll need to look at the description of the contents of the tablet to confirm that it has calcium hypochlorite as the main ingredient. Also need to be prepared for misleading labels for the calcium hypochlorite tablets. A couple of labels for these tablets at home improvement supply stores are shown below. Drain cleaner drop-in tablet. How's that for clarity? Did you ever think drain cleaner? Yeah, right. You're not cleaning anything other than you're cleaning up the effluent maybe. How about aerobic septic tablets? That's a contradiction in terms, aerobic and septic. But those are some of the misleading titles they have. So it could be a little challenging to go find these calcium hypochlorite tablets in your home improvement store or hardware store. So that completes this presentation. And what I would like to suggest, and I should have mentioned it earlier, any questions you have, use the question box and fill them out. And what I want to do, I'm going to go through my presentation on explaining the chlorination process, the calculation, and our Excel spreadsheet, and then we'll just tackle the questions at the end. So let's go here. One. Go up to the top, select it. As I mentioned earlier, when I looked at the design reports, I saw that basically a focus on calculating how many tablets would be utilized by an on-site system. And so I wanted to look at that calculation process in a little bit more detail and then explain some things there. So let's do a little problem description. So we're going to look at an example of a chlorine disinfection calculation and associated explanation. So disinfection is going to be provided by an erosion type tablet chlorinator using calcium hypochlorite tablets. With this type of chlorinator, the levels of coliform bacteria should be reduced to a log to the base 10 value of 0 for the coliform concentration in CFUs per 100 milliliters, which is, by definition, nominally free of coliform bacteria. In other words, if you have 1 CFU or less, you got a log value of 0, and the effluent is nominally free of bacteria. Now, the available chlorine concentration for disinfection purposes is specified in Arizona Administrative Code R18-9-E320 D1A for a given level of wastewater treatment. See Table 1 for reference, and that's Table 1 of the presentation, not end rule. We're going to assume that the pH is 7 and that the wastewater treatment produces an effluent with a total suspended solids value of 20 milligrams per liter. Now, the Arizona Administrative Code specifies that a minimum dose of 10 milligrams per liter is required. Unfortunately, typical tablets deliver a dose of 9 milligrams per liter. Therefore, the typical design will require a double tablet feeder in this example. So the chlorine demand will be in the range of 1 to 5 milligrams per liter. A value of 5 milligrams per liter will be selected for this example. See Table 2 for reference, and we're going to look at Table 2 coming up, and that's Table 2 of this presentation. So first, here's Table 1. And the title in Arizona Administrative Code is basically concentration of available chlorine for wastewater. That's another way of saying that's the chlorine dose. And in this case, let's look here. We're looking at a pH of 7. And so we have a total suspended solids value of 20, and therefore it says the dose is 10 to 20. Notice qualitatively, I'd said earlier that as your pH is reduced, your chlorination process is more effective. Notice that the dose only needs to be 6 to 10 if you got water with a pH of 6, and then it goes up 20 to 35 if your water has got a pH of 8. Okay, now let's look at the chlorine demand and dose guidelines for wastewater. So our wastewater source here, and this table actually has information for a variety, including septic tanks, but septic tank effluent. But what we're using a higher quality effluent where it's a packed bed filter effluent where the dose of the demand, the typical demand is 1 to 5 milligrams per liter. And the recommended dose, again, you see it's 10 to 20. We're going to have a pH of 7. All right, let's see how we do this, work out this calculation now. So the chlorine residual is going to be calculated, but a residual of 1 milligram per liter is desired to achieve good disinfection results as per a study done by the University of California, Davis. So the following formula is going to be used. Simple, very simple formula. So the chlorine residual, get my highlighter. So the chlorine residual is equal to the chlorine dose minus the chlorine demand. So since we have a double tablet, double stack, so we're going to have two 9 milligram per liter tablets. It's 18 milligrams total minus 5. So our chlorine residual is 13. And that chlorine residual in this case is going to be equivalent to free chlorine residual. Now, the Arizona Administrative Code specifies a minimum contact time of 15 minutes. However, the contact time needed for effective disinfection will be calculated and compared to the time specified in the AAC. In drinking water systems, a combination of chlorine, residual, and contact time is used to determine whether effective disinfection has occurred. And the following formula is used. Now, let me just comment. The Arizona Administrative Code here is prescriptive in orientation. And so there's some conservatism built into it because a variety of conditions could be present. And you need to take that into account. And so I believe the writers of the rule here, Arizona Administrative Code, were being conservative to take into account these various unknowns and variables. So the formula that we're going to use is effective disinfection, ED is equal to C, chlorine residual times time in minutes. Now, a value of 6 milligram per liter minutes is a value that is commonly used to confirm that good disinfection is occurring. I'll pull that from drinking water. Therefore, the calculation for effective disinfection is shown below. Rearranging the formula to solve for T, it is now time in minutes equals effective disinfection divided by chlorine residual. So in this case, you have 6 milligram liter minutes divided by 13. So T is equal to 0.46 minutes required with a double tablet chlorinator. So you can see you're going to get disinfection very quickly if you have good operating conditions. Now let's calculate the number of calcium hypochlorites used each day for this double tablet chlorinator. So we're going to assume a design flow of 450 gallons per day. We're going to assume a chlorine dose of 18 milligrams per liter because we had a double tablet chlorinator. So then we're going to calculate this in metric. So we're going to convert, again, we're going to go 450 gallons per day. We're going to convert that to liters, 1,703 liters. Our tablet consumption, we got 18 milligram per liter dose of chlorine. However, calcium hypochlorite tablets are not pure chlorine. They've got binder in it. And their chlorine is rated at 70% available chlorine in that tablet. Therefore, we got to come up with the milligram per liter tablet dose. So divided by 0.7, you get 25.76 milligrams per liter. So then the weight of the tablets used per day in milligrams per liter. So you got 1,703 liters times 25.71 milligrams per liter gives you 43,798 milligrams per day of tablet. So then the number of tablets used per day. So we have 43,798 milligrams divided by 1,000 milligrams per gram divided by 140 grams per tablet, and you're using 0.31 tablets per day. All right, so now let's do this an easier way. We're calculating tablets. So, let me bring up a spreadsheet that you can use. All right. So the two numbers shown in blue are that's your input. And so the first one is your plant flow in gallons per day. And so you just enter whatever value. In this case, we're going to use 450. And then this is the chlorine dose. In this case, it was a double tablet chlorinator. That was 18 milligrams per liter. And then you get your results shown in yellow. And so your plant flow in liters per day, your tablet dose, the weight of tablets used per day, the number of tablets used per day, the pounds of tablets used per day, pounds of tablets used per year, number of tablets used per year. And of course, now if we change that to 9, then it drops, so you can see I'm only using 57 tablets per year. So it adjusts everything accordingly. Now notice I put down a note 1, tablet consumption is based upon the effluent flow through the tablet chlorinator, the chlorine demand, and the ability of the tablet to dissolve at a rate that will produce the chlorine dose specified and needed. And that's real important. And of course, the tablet has to be there. This is probably one of the biggest challenges associated with the tablet chlorinator is somehow when the tablets are all consumed, they don't get the stack, tablet stack doesn't get refilled. And that needs to say is a problem. So let's see if we have any questions. Let's see. Questions, throw those out. Okay. Okay, so here's one from Ashley. With regards to pool tablets, generally also contain cyanuric acid, which at a certain ppm will lock up free available chlorine, making their purpose mute until cyanuric levels can be eliminated. But also imagine if a residual of cyanuric acid builds up in the system and soils, this could create other negative effects. Don't have research on it, but I thought it would maybe food for thought for you. The more reasons we can give people not to use pool, the better. Okay, can we get a copy of the Excel spreadsheet? Absolutely. Everybody will be able to get that. My thought right now is just that we post it up on our website along with the presentation. And then you could just download it, and it's free of charge. And you can quickly check the submittals and the design reports. So with that, I will conclude, and I appreciate your attendance, and hopefully you've learned something and will be beneficial for you. Thank you.